Hello and welcome to another Java tutorial. In this tutorial, I'm going to talk about one very interesting thing about numerical integration. So far we have discussed 1D, 2D, and 3-dimensional integration of functions, and now one question that remains is this. Assume that we define an integral function. So f of x is a given function, and we define g of t, which is an integral function for f, which means we are integrating f from some initial value a for x times some variable t. All right. So if I want to find the value of g at some point, I have to integrate f of x from a to that point. All right. So this is called the integral function or antiderivative. Then we already know that the fundamental lemma of calculus for one-dimensional function is that if g is an integral function of f, then d dt of g equals to f of t. All right. So g is antiderivative. So if we take the derivative of g, we should get f. That's the thing. But then the question is, all right, g is defined as an integral of f. So how to find the g of t over an entire interval from a to t1? So I want to find, for example, g at 1000 points inside this interval. Obviously, option 1, which is the naive option, is to just simply, for each value of t, we do the integration from a to that value t, all right, for each t. So if I want to get the value of g at 1000 points, I have to do 1000 integrations, all right. So that's not a big deal. We have to kind of do it at the end, but the problem is that if t is very large, let's say this t1 end of interval is very large, then when we get to the last points, then the interval becomes very large. That means that we have to increase the number of subintervals. If you recall, in the integration, for any method that we did for numerical integration, we said that we have to divide the original interval into subintervals, and in each subinterval we do Simpson or Gauss-Legendre or Newton codes, interpolations or quadrature rules. So if the end of interval is very large, then for the last points, let's say 100 last points, if I'm calculating 1000 points, the cost is become very large, right? The cost of integration. Now the second option is that, okay, instead of doing numerical integration, I numerically solve this differential equation, and that's also an option. And remember that for any first order differential equation, we need an initial condition, and based on this definition, we know that if g is evaluated at a, then we are integrating from a to a of f, and integration of a to a is always 0. So the initial condition is g of a is 0. But then the problem is that this is not a nice way of doing this, because we are actually changing the problem that we're trying to solve. The problem is to calculate this integral for 1000 points in the interval of a to t1. Even if the t1 is very large, we want to do this calculation for 1000 points very efficiently, all right. But we are changing the problem and saying, okay, go and solve the differential equation. That's one thing. So we do not want to change the problem. The other thing is that solving differential equations using higher order approximations is usually costly if we want to get good accuracy. All right. So what we want to do eventually, we want to stick with our simple integrating approaches, Gauss-Legendre, Simpson, these kind of very simple approaches or methods. But we want to be able to efficiently calculate g over very large intervals for many number of points, let's say 1000, 2000 points. So what I'm going to do here, I'm going to introduce a third option, which is called memoized integration. So what do I mean by memoize? So memoization is a term which we usually hear in computer science. And I've taken this definition from Wikipedia. So it says that in computing, memoization is an optimization technique used primarily to speed up computer programs by storing the results of expensive function calls and returning the cached result when the same inputs occur again. So how do we apply this to, for example, our problem of calculating the g of t in 1000 points over the interval? Is that we use the breakpoint property of integration. So let's say I calculate the g at some point t1, all right? And then now I want to calculate the g at another point t2, where t2 is greater than t1. So I can write the integral of from a to t2 as a sum between a to t1 and t1 to t2. Now t2 could be very large, t1 could also be very large, but t1 to t2 could be very small or small enough, right? So if I already have calculated the integral from a to t1, in order to calculate the a to t2, I store the result of the integral a to t1 at somewhere, and then I only add the result of integration from t1 to t2, from t1 to t2 to the previous one, all right? So when I start to do if I want to calculate g of t at 1000 points, I start from the first point, and then second point, third point. For example, for the fourth point, I only calculate the integral of f from the third to fourth point, and then add it to the previous result, all right? So this way we are very efficiently, and the key here is that to make sure that the difference between the two steps, t1, t2, from t1 to t2 is small enough so that we can just simply apply a Simpson method or Gauss-Legendre quadrature method, okay? So this way we keep the accuracy regardless of how big the interval is. We always keep the same accuracy in all the steps in calculating the value of g at each t point, at point t, right? Because the only thing that we're adding in each step is this extra integral, which is the interval is very small, all right? And we can use a data structure in Java such as list or map for memoization, for storing the results. So let's go to Eclipse and try to implement this memoization technique for integral. So we have this demo integral, and here I'm going to create a new package. Let's call this Memoize. And here I'm going to create a class memoized integral. Okay, here obviously we have an integral function 1D func, that's our function f, and we need to import this. And then we have a constructor public memoized integral, and let's call and the input is basically the same. We just pass in the function and also double start. Okay, so we have to also know what the start point is, double start, and then this dot func is func, this dot start is start. All right, so how do we implement the memoization? So we can, first of all, we can have a setter for, so public void set start double start, this dot start equals start. Okay, so and we're going to have a method public void calculate, or yes, calculate. And then what we want to do is we want to have int number, num points, or number of points, okay? So we want to say, we want to let the user set the number of points that he or she wants to calculate the function at over the interval, right? And oh, okay, maybe also we need to have an end, so we have to specify the entire and yeah, so we can specify the entire interval, or we can specify just here. And okay, let's specify it here. So double end and integer number of points. Okay, so what we want is but again, because this is an object, it's going to store the data, so it's better that these parameters don't have any this method don't have any parameters. So and then we're going to have a setter public void set end double end this dot end start end equals end. Okay, and then we're going to have an integer number of points, and we're going to give it a default value of 100. Okay, and then we're going to have a setter for it, public void set number of points int number of points, and this dot number of points is equal to number of points. All right, so this is the assignment. And okay, so we can also remove these, because then the user can just use the setters to do it. But okay, so let's just focus for now on the calculation. How do we do the actually implement the memoization? Implementing memoization. So we're going to create an array. So let's say let's use hash map, for example. So map integer and double let's call this cache. So we're going to do the caching. Okay, and let's import the map from Java util. So we're going to create our hash map in the constructor, for example. So cache is new. I'm going to use a hash map, and it's automatically going to infer that. We actually don't need this, right? Because it's going to automatically infer the type, but let's just keep it. Okay, and then we have the cache, and the cache is originally empty, so empty cache. So what we are going to do, we're going to break the interval into some points, right? And based on the number of points, we're going to do the integration. All right, and let's say that we want to have the okay, so delta, let's define our delta. Double delta is basically end minus start divided by number of points. Okay, and then what we are going to do for int I equals 0, I less than the number of points, I plus plus, we are going to do the integration. All right, and then basically and so integrate from basically let's see, double t start or maybe let's call it t1 is start plus I times delta double end, or t2 is basically start plus I plus 1 times delta. Okay, and so this should be okay, that's correct. And then what we want to do, we want to integrate over t1 t2. So the result, so here we want to this for in each step in this for loop we are calculating integrate over the start to the value t, okay, which is t2. This is the end, okay, t. Let's call this t. And then what we want to do, we want, if instead of integrating this, what we want to do, we want to basically only integrate, basically the result in each step should be the result in the previous step, right, from start to t1. t1 is one step before t, and okay, let's maybe remove this. Let's call this I, or I plus 1. Okay, so and plus we just integrate from t1 to t2. Let's call it t2, doesn't matter. Okay, so we just want to do this, and we're going to add the result, our cached result from the previous step. But in order to do that, we're going to test. So if cache contains key, let's say I, if index I is available, which means we already have calculated this from start to t1. So we just say that, okay, double result is basically cache get I, right, result of previous step plus new integral 1D, pass in our function Gauss Legendre from t1 to t2. Okay, so we're just integrating from t1 to t2. And the thing is that we don't want to, so in this Gauss Legendre, we're dividing by 100 sub-interval, which defeats the purpose. So what we are going to do, I'm going to call, for example, Gauss Legendre 5 point, t1, t2, all right? I just do the 5 point without any subdivisions. So this is the result. Now we get the result. We're saying that, okay, and now we need to put this back into the cache. Okay, so cache dot put index I, the value is the result. So that's our cache. So if the cache doesn't have index I, which means the index I has not been calculated. So what we are going to do, we're going to basically calculate it. So the same thing, but here the integral goes from 0 to t1. Okay, so that's how we calculate the cache. And let's double check, see what's happening. So we start from I0. Okay, at I0 t1 is a start, t2 is a start plus delta, and then the cache is empty in the beginning. So we go here and we calculate from 0 to from start to t1, okay, which is basically 0. Actually, we should calculate from t2, or t1. Okay, so in the beginning it's 0, right? From if t1 is the beginning of the interval, which is a start, so integral from start to start is 0. So the integral, so then for I0 which is the start point, the result is 0. We put it there, and then we go to the next step, which is I equals 1. T1 is start plus delta, and T2 is start plus 2 delta. So I guess then we check if cache contains 1. Actually, this get also should also be I minus 1, right? So what we are doing here is so at I0 actually when we have the previous step is I, so the next step is I plus 1. All right, so if I is 0, we have a start plus delta, and then so I is the current step, so we have to look at I minus 1. We put I. So if I is 0, we go here, we put I, okay, correct. And then I becomes 1. T1 is start plus delta, T2 is start plus 2 delta. So I guess this should be I minus 1 and I. And then I is 1, start plus delta, cache contains 0, correct, so we get the result from previous step, and then we integrate and we put it there. Now both of the results of I equals 0 and I equal 1 are in the cache, and then I becomes 2, start plus delta, T2 is start plus 2 delta, cache contains 1, so we go here, we retrieve it, plus we integrate from T1 plus T2 and put the value of 2. Okay, all right, so this works, so this caching works. And then we can also have an array, so public double, for example, get result or get results, and here we can convert the map, so we can say double values or result is new double number of points, and for int I equals 0, I less than number of points, I plus plus results I dot results I equals cache dot get I, and then return results. Okay, now we can go and test it. So test class test memoization, we're going to have a main method here, and here I'm going to call test1, and let's create test1. In test1 I'm going to have integral function 1D, and let's call it func, and here t goes to t sign up math dot sign up t. Okay, we need to import this. Okay, and then we're going to have a memoized integral, memo new memoized integral func, and then we're going to start from, let's say, 0 to 200. So that's a fairly large interval from 0 to 200. Okay, and then what I'm going to do, I'm going to try to plot it. So MATLAB chart, fig, new MATLAB chart, and then fig.plot xy. So what I'm going to do, these are the results, and public double get points, and for the points we just do a for loop, double x or points, new double number of points here, and then delta is this for int I equals 0, I less than number of points, I plus plus, points I equals start plus I times delta, and then we're going to return points. Okay, and then x, so x is memo get points, y is memo get results. Okay, and then after we create the memo we have to call the calculate, and then fig dot render plot, fig dot show. Okay, now I need to go to the run configuration, and in the arguments I have to uncheck this, and that's a bit odd that we didn't get anything. Why? Let's uncomment this. Maybe let's plot 2 for example. Let's see. Still nothing. N minus start over number of points. Okay, that's because we're dividing by, okay, these should be double, we have to be careful here. Still nothing. Let's see. All right, let's look at the values. So sysout arrays to a string of some to a string memo dot get points. So let's check if the points are correct. Okay, so that's because everything is 0. I less than number of points. Why is everything 0? Points I is start plus I delta. So that means delta is 0. But why is delta is 0? Because we forgot to initialize the end. Okay, so now it works. All right, from 0 to 1.98, and the problem is that the 2 is not included. So what we need to do is okay, so let's try to plot it one more time. Yeah, that looks, let's maybe try to do t. So t is linear, so its integral function should be a quadratic. At 0, at 2, we should end up with the, so the integral function is t squared over 2. So we should end up with 4 over 2, 2. That's correct, right? At 1, we should end up with 1 over 2, which is 0.5, right? Now the thing is that here I can increase to 20. At 20, I should end up with 20 squared, which is 400 over 2 is 20. And it was still pretty fast, okay? And so, and then let's go 200. At 200, I end up with 40,000 divided by 2, it's 20,000. And it's pretty accurate, okay? Now let's try to do this without memoization. And recall that with memoization, we're getting a pretty fast result, right? Over this large interval. If we didn't do memoization, so private static void test2. Test2. In test2, what I'm going to do, I'm going to just do naive integration. Naive integration is that, okay, we have the same thing here. We're going to plot the stuff, but we're going to have double x is basically Matthew Thiel's linear space from 0 to 200, and we're comparing with 100 points that we had, and then double y is basically new double x dot length, and then for int I equals 0, I less than x dot length, I plus plus. What we are going to do, we're going to say that, okay, yi is the result of integrating of our function from, and remember in the memoization we're using 5-point Gauss-Legendre, right? So let's exactly do that again. Gauss-Legendre 5 points, and the start is basically x0 to xi, okay? So this is the naive integration. We're just integrating from a start point to the sum point inside the interval that we want to have, and we want to have 100 points. So we're doing 100 integration without any caching, right? And then we're going to plot it. So everything in these two cases are the same. So let's see. It still works fine, right? And what we see here is that it wasn't that, so let's also add timers for the integration for the whole thing maybe. So timer new timer dot start, and then we're going to do timer dot stop and timer dot show. For both cases here. Actually, I'm going to put it after, okay, yeah, maybe just everything. So the naive test 2 is the naive approximation 48 millisecond. Let's see test 1. It's 50 milliseconds. So in this case, it's really not that much of a difference, right? But if we increase to 2000, for example, here, so running test 1 with memoization, maybe run both of them. Memoization 48, and then the non-memoization is basically 1 millisecond. Let me see why this happened. So if we just run test 2, it's 48 milliseconds. So there is some delay because of just launching the application, setting things up, right? Loading the class into the memory. But there is not much difference in this case between test 1 and test 2, which means with memoization and without memoization. But there will be many cases that maybe let's just change the function to something more t times math.sin of t. This is our, let's make this as our final comparison, math.sin of t. So first thing is memoization, 50 millisecond, and again I changed the function, but the duration didn't really change because caching, putting things in a hash map and retrieving it back is a constant time. It doesn't really depend on the basically the interval or the function that we're using. So 50 millisecond for test 1 with memoization. Let's see how much. 48 millisecond with but you see the problem here, right? Without memoization, the problem here is that this is wrong, right? Because we're doing 100 points, but the problem here is that when the interval becomes very large, 0 to 2000, so around here, with only 100 sub-intervals, we cannot have a good approximation. That's the main problem. And in order to increase it, increase the accuracy, we have to go 1000. So let's do this. So memo.set number of points 1000. And again 1000 it still does maybe okay, so let's reduce the interval to 200, but we're testing with 1000 points. It takes maybe let's just reduce the interval to 20. So we're doing 0 to 20, but with 1000 points. And this is without memoization, with memoization. Okay. Now what's showing here is that there is something going on, right? Because let me see. We have -2, this goes up to 35, this goes up to 16. So there's definitely something different between the two, right? And so in with memoization we get this function. Without memoization we get this function. So let's compare them. Yeah, for small ones it seems to be correct. At 12 it's -15. Here we get about here we get about -14. Here we get about -12. So one of these is not correct. So let's see. Let's increase the value here to 2000 points, and we're running test 2. it still seems to not change much. So let's try to do the here 2000. Now it seems to be similar to the previous result. Okay, and as you can see, basically the time for memoization doesn't really change that much, because even if the interval is very large. Let's go 200. The result 54, and now let's try test 2. 52. And you see the problem, right? So this is with memoization, and it's the correct result. Without memoization, you see it's all incorrect for right around here, right? We definitely don't get a good result. So in order to get a good result, without memoization, we have to increase the number of points, 5,000 for example. And again, it still doesn't work. 10,000 points. Still not good enough. 20,000 points. Still not good. So there seems to be, let's say 100,000 points. No, it still doesn't work. So in this case, because the interval was very large, this naive approach completely failed. We cannot get any good result. And but the memoization gives us a very nice good result, and it's pretty fast. So with 2,000 points, we're getting about 50 millisecond, 56 millisecond. With 5,000 points, we get about 60 millisecond, and it's pretty fast, pretty accurate. This is the most accurate result, okay, for integrating the function. All right, thank you for watching. I hope you enjoyed this, and I'll see you in the next video.